Hello everyone. In this chapter, we're going to talk about the waiting lines and the queuing theory models. Queuing theory is the study of waiting lines, one of the oldest and the most widely used quantitative analysis techniques. You must be familiar with the waiting lines. For example, you go to McDonald's, you see a waiting line. If you go to Walmart, you also see the waiting line. So you can see the many waiting lines in reality. This is why waiting line models are very important for business. And then we have to study queuing theory. So in this chapter, we're going to talk about some of the basic concepts and the basic definitions, also basic techniques regarding queuing theory. Basically, we'll focus on the waiting line models. We want to know how to minimize the waiting cost and also service cost. Then we can achieve uh, efficiency with a certain level of customer service. So this is a basic objective for this chapter. Then for the waiting lines, you need to know three basic components: arrivals, service facilities, the actual waiting line. We need to collect the data and analyze the data and to get the useful information regarding the waiting lines. But basically, we have objectives. The two objectives. The first one is to maintain a certain level of customer service. The second is to minimize the total costs. We're going to talk about this later. Later on, also, I'll give you an example regarding how to minimize the total cost, including service cost and the waiting cost, and also how to determine the number of service facilities. That's about the level of the customer service. Let's look at the cost, waiting line cost. Most waiting line problems are focused on finding the ideal level of the service a firm should provide. We should look at the customer the service here. But you should know that some conflicting objectives regarding the waiting line costs. There are two extremes. For example, a large staff and many service facilities, high levels of service but high costs. And then the minimum number of the service facilities. Service cost is lower, but it may result in dissatisfied customers. So basically, we talk about these two conflicting objectives here. We want to increase the level of customer service, but there may be high cost. If you want to reduce your cost, you may have unhappy customers. So we needed to get a trade-off between these two conflicting objectives. So this is why we want to minimize the total expected cost, and then we can achieve a certain service level. Right? Or we want to find a service level that minimizes the total expected cost. Let's look at this picture. You can see this graph, right? Horizontal axis shows the service level, vertical axis show the cost. We want to check out the relationship between the cost and the service level. You can see here there are two kinds of the cost: the service cost and waiting the cost. And then we have a total cost. We add the cost of the services and cost of the waiting together. That will be the total expected cost. But you may notice as the service level increases, the cost of waiting time decreases, and the cost of providing services is increasing. So, so when we add up the two the costs, and then we got the total expected cost curve. So this is the curve. We want to minimize the total expected cost, right? And then you may notice this intersection between these two, uh, the costs, this is the intersection. And then you can see this is the optimal service level with the lowest expected cost. So this is the way we wanted to understand how to determine the optimal service level with a minimum total expected cost. But also this is not accurate. We should use another method to calculate the total expected cost or the total the cost for providing services or total cost for waiting time, and then you can figure out the optimal service level. Okay, let's look at an example how to determine the the number of the servers. Three Rivers Shipping Company operate a docking facility on the Ohio River. An average of 5 ships arrive to unload their cargoes each shift. Idle ships are expensive. The more staff can be hired to unload the ships, but they're expensive as well. Three Rivers Shipping Company want to determine the optimal number of the teams of stevedores to employ each shift to obtain the minimum total expected cost. Now, how to figure out the, the optimal number of the teams of stevedores? So we're going to look at this problem. We use this chart. You can see we list some the information here. Let's look at this part first. Uh, we want to list the number of the teams stevedores working. Could be one, could be two, could be three, could be four. But for each number, we want to calculate the average number of the shift arrival per shift that's given, and average time each shift waits to be loaded, the hours. And then total ship hours lost per shift is $35. And then we use the 5 times 7, $35. Estimated cost per hour of the idle shift time is $1,000. And the value of the ship, the lost time or waiting cost, C times D. Let's see the total ship hours lost per shift, estimated the cost per hour of the idle ship time. So this is the 1,000 times 35 is 35,000. And then stevedore's team salary or service cost is $6,000. And then we needed to add E and F. You can see, and then we can have the total expected cost, $41,000. Similarly, you can calculate for number 2, number 3, number 4. Then you can get a different total expected cost. And then I need you to determine which one is the lowest. Okay? It's very obvious to see is this one, right? This is the lowest uh, total expected cost. And then you go up to see this number is 2. So what is optimal service level? Or here, what is the optimal number of the teams of stevedores working is 2. So we use this method to figure out the optimal service level. Now we want to look at the characteristics of a queuing system. We talk about 3 parts to the queuing system. Arrivals, we input. Also, we call the calling population, the queue or waiting line itself, the service facility. And then you should know we want to use the different characteristics to understand this the queuing the system. And then we want to do the calculations. We want to determine the optimal level of service, and also we want to minimize the total expected cost. For arrivals, we needed to know 3 major characteristics: the size of the calling population. This population could be unlimited or limited. Or also you understand the pattern of arrivals. Arrivals could be random, it could be the constant, based on the different scenarios. If the arrivals are random, so they follow a Poisson distribution. We already reviewed the Poisson distribution in chapter 2. If you don't remember what is a Poisson distribution, I highly suggest that you go back to check it out in chapter 2. Also, we should look at the behavior of arrivals. The most queuing models assume customers are patient and will wait in the queue until they are served and do not switch lines. But also, we have some other kind of customers. We call the balking, refers to customers who refuse to join the queue. Also, we have other different kind of the customers, reneging customers enter the queue but become impatient and leave without receiving their service. But we just look at the first kind of the customers. Okay? We don't look at the balking customers, the reneging customers. For a waiting line, Waiting line could be limited or unlimited. And also we should look at the queue discipline. Queue discipline refers to the rule that which customers in the line receive the service. For example, we may use the most common rule, first in, first out. Also, you have other rules. But in this chapter, we just focus on the first in, first out, FIFO. And then for service facility, you also need to look at some characteristics. For example, we want to look at configuration of the queuing system, single channel system, only one server, multi-channel systems, multiple servers, fed by one common waiting line. Pattern of the service times, the single phase system can receive the service from just one server. A multiple phase system, customer receive the service from multiple servers. Let's look at some of the pictures for the queuing system. Let's look at the first one, the single channel, single phase system. Arrivals, the queuing system service facility, departures after service. This is very common in reality. For example, you go to the McDonald's, you can see the service facility, one service facility, one waiting line. Or we have the single channel multi-phase system. This is very common in the drive-through windows. For example, you go to Dunkin' Donuts. First of all, you need to speak to someone with speaker, and then basically at this phase, you need to make choices, and then you may want to buy the coffee, you may buy the donuts, but you should place order here, and then you're going to receive your order. It goes to the drive-through windows, and then depart. So this is like a single channel multi-phase system. And also another kind of the queuing system configuration, the multi-channel single phase system. If you go to Bank of America, you can see different the tellers right there, and they provide the same services. Okay, and so this is like this. Or we have the configuration of a queuing system like this. Rivals the queuing system here. So they have the first the phase and the second phase. This is very common in hospitals. The multi-channel, multi-phase system. In this chapter, we just focus on single channel, single phase system. And now we want to talk about the service time distribution. We already know about exponential probability distribution in chapter 2. Again, if you don't remember or you don't understand it, I highly suggest you go back to check it out. And the service patterns could be constant or the random. Uh, in most cases, the service times is random, but we assume service time follows a negative exponential probability distribution. We need to collect the data, plot the service time data, and then we want to figure out the right probability distribution. But in most cases, we assume service times follow a negative exponential probability distribution. And also, you can use your data to verify service times probability distribution. We wanted to use the notations called the candle notation to represent the queuing system. So basically, you can see here, we use 3 symbols: arrival distribution, service time distribution, number of the service channels open. You need to know some notation here. M stands for Poisson distribution for number of occurrences. D stands for the constant rate. G, general distribution with known mean and variance or standard deviations. So I like you to understand this candle notation, and you also know how to read this notation, how to use this notation as well. Now let's look at some examples for candle notation. For example, look at MM1. This is a single channel model with partial arrivals and exponential service times, right, like this. If you add one more channel, just MM2, or you can do like this. You add one more channel, but the service time that follows the constant pattern. So this the service time is constant. Use MDF3 to do this. Or you can have the fourth channel. You put a 4 right there. And for arrivals follow Poisson distribution. Um, but the service time follows normal distribution. We use MG4. As I said, we focus on MM1 in this chapter. So let's look at some assumptions for this model. Arrivals are served on a FIFO basis. There's no bulking or reneging. Arrivals are independent of each other, but arrivals rate is constant over time. Arrivals follow a Poisson distribution. Service times are variable and independent, but the average is known. Service times follow a negative exponential distribution. Average service rate is greater than the average arrival rate. So these are assumptions. They are very important. I like you to understand them very well. And then we can go to some equations. Right? Before I talk about the queuing equation, we want to introduce some notations. Lambda refers to the mean number of arrivals per time period. Mu stands for mean number of customers or units served per time period. So you should use the same time period for arrival rate and service rate. This is very important. When you try to do the calculation, you should be careful with this. Now let's look at those equations. The first one, the average number of customers or unit in the system. L equals lambda divided by mu minus lambda. Number two, the average time a customer spends in the system. W equals 1 over mu minus lambda. The average number of the customers in the queue, LQ. Now you may notice this L, this is the LQ. So this is for system. The system includes the levels, the queue, and service. But for the queue, we just look at the queue. So queue is one of the parts of system. So they are different. Right? So when you try to use these formulas, you should know the differences among them. Number three, the average number of customers in the queue, LQ equals lambda square divided by mu times parentheses, mu minus lambda parentheses over. Okay? And then number four, the average time a customer spends waiting in the queue, WQ. Again, this is about the queue and not about the whole system. The WQ equals lambda divided by mu times the parentheses, mu minus lambda parentheses over. Number five, we also can calculate the utilization factor for the system, denoted by rho, the probability the service facility is being used. And we just rho equals lambda divided by mu. You need to get familiar with these equations or formulas because we are going to have the questions on the test for using the formulas. And you need to know the differences between the system and the queue. Also, number six, the percent idle time, P0, or the probability no one is in the system. Also, we can calculate the probability no one is in the system. You should know this formula. The B0 equals 1 minus lambda divided by mu. So what is lambda divided by mu? We should go back. Is utilization factor. So in order to calculate the percent idle time, or the probability no one is in system, you just use 1 minute utilization factor. Number 7, the probability that the number of the customers in the system is greater than k, p can greater than k. So we use this formula. So this the lambda divided by mu exponent of k plus 1. Be careful here, this k plus 1. Okay. Let's look at an example. This is about Arnold's muffler shop. Arnold's mechanic can install mufflers at a rate of 3 per hour. Customer arrive at a rate of 2 per hour. So we can figure out the values for lambda and mu. Lambda equals 2 cars arriving per hour. Mu equals 3 cars serviced per hour. And then we can calculate L and W, and also we can calculate LQ, WQ, rho, and P0. Further, we can calculate the costs. So here we talk about some of the costs here. We want to evaluate especially the cost, including the service cost and also waiting the cost. And then we want to determine the number of the servers, or here we talk about the number of the workers. Uh, Now let's look at the total service cost. The total service cost equals the number of the channels times the cost per channel. So we use M times CS. Here M refers to number of channels. CS refers to service cost of each channel. This is service cost, but also we need to look at the waiting cost. We want to look at the two kinds of waiting cost. The first one is based on the time in the system. The second one is based on the time in the queue. I'll look at the first one. The waiting cost is based on the time in the system. The total waiting cost equals the total time spent waiting by all arrivals times the cost of waiting. The number of arrivals times average the waiting time per arrival, C times CW. And then you can see the formula right here, the lambda times W times the CW. If the waiting time the cost is based on the time in the queue, you should use WQ to do calculations. Okay, now we want to put them together. Okay, so the first one is about the total cost based on the time in the system. So total cost equals the total service cost plus the total waiting cost. M times CS plus lambda times W times CW. If the if it's based on the time in the queue, the total cost equals M times CS. Okay, this is the same, but you should use WQ instead of W. So this is very important. You should pay more attention to this. Now we can plug all numbers into the formulas. So we can see here, the first of all, we want to know just the cost of customer waiting time in the line is $50 per hour. Now we can calculate total daily waiting cost, 8 hours per day times lambda times lambda q times CW. And then you can see here is $533.33 per day. And also we will look at the service cost, the total service cost, 8 hours per day times M times CS. But we know the mechanic's wage is $15 per hour, and then we can calculate total daily service cost, 120. And then you can calculate total cost for the system, right? You can add them up, and then you can get the total cost. Here again, you can try different number of channels and to see which one is optimal, like what we did before.